You okay there? How about you, Tom? You ready? So we've been talking about externalities, and there's a couple of them that I didn't finish up, and one of them is regulatory externalities. And remember, externalities are the things that we have to do as part of today's environment for engineering. You can be the greatest technical person in the world, but you're going to find that you're limited and you have constraints placed upon you by society in a whole number of areas, and we talked about some the other day. One is regulatory, and we've got pictures here of solar cells and wind turbines. Could have a picture of hydroelectric power. Essentially, a number of states in the United States and parts of Canada have regulated that by 2025 or some date, they will have 20 or 25% of all their electricity generated by renewable energy. And this is because of people's concerns about global warming and whatnot. Well, it turns out this is an example of wind turbines. For example, in Texas, they have a tremendous amount of wind. They've been talking about the wind coming through Texas with Hurricane Harvey and whatnot. But in West Texas, it's nice and flat, and they got wind. In fact, Oklahoma, just north of Texas, was known for all the wind they had as a constant source of energy essentially blowing through. And so it turns out Texas passed a law like this, and essentially American Electric Power has gone in and spent $1.2 billion building wind turbines. Okay, they have not yet built the transmission lines that are going to carry the wind turbines to Austin and Dallas and stuff, because nobody in West Texas, so the cows don't need that much electricity, okay? It's just ranch land and stuff. We have solar power. You drive down the highway, the interstates now, and you'll pass these big solar panels. I have 10 kilowatts of solar power on my roof now that I redid my roof this year. And what this does, aside from improved global warming, it also raises everybody's electricity rates by about 50%, okay? So we can legislate and regulate and say that we're going to have more environmentally friendly sources of energy, but it turns out it costs money. Another thing, type of externality, is intellectual property. And the story I have here on intellectual property is that General Electric patented a nickel-based superalloy called GTD 111 in the mid-1970s. And it became part of a lot of their land-based turbines, and in some cases it's part of aircraft turbine engines and whatnot. But starting in the 1980s, as the patent was, or 90s, as the patent was expiring, other people realized this was a good alloy, had good high temperature properties, and they started designing it into their engines. So far as that goes, the problem became that in around 1980, General Electric applied for a patent and on the heat treatment of this alloy. This is a successor patent. And it turns out that the patent office kept refusing it for almost 20 years. But GE's attorneys were persistent. They'd keep on rewriting it. And finally, in the late 1990s, the patent office issues this patent 20 years after it had been applied for. And everybody else has thought this was a public domain alloy. They had designed it into their system, and all of a sudden, General Electric re-owns the rights, okay, for another 20 years. So there's a big scurry to find replacements or to develop ways around the patent, because General Electric was going to gouge people on their patent rights. So another one, this actually came to me from a student who took this class 3 years ago. She had worked for an oil company down in Houston one summer, and there was a project they wanted to do, an oil country project that had very corrosive crude oil, and they were trying to decide whether they could use carbon steel or clad steel, and was the clad steel required for corrosion resistance? Well, it turns out the technical decision was the carbon steel would corrode too quickly, and you really needed to have clad steel pipe. But the country where they were going to do this, and she never told me the actual country, but basically required offsets. And offsets on major projects are because these countries would like to create jobs within their country. Boeing faces this all the time. Airbus faces this all the time. Some country in Africa or South America wants to buy commercial aircraft, and they'll say, well, we will buy $3 billion worth of airplanes, but we want 5% of the work to be done within our country. Well, there's only so much that Boeing can give out. Certain things like the wings are pretty critical, and Boeing wants to keep those right here in the United States for various reasons. But it's not so bad when Japan buys $10 billion worth of aircraft, because there's plenty of high-tech companies in Japan that can build fuselage parts and stuff for Boeing. But in some of these other countries, it becomes a problem. And it turns out this particular country required a certain percentage of all the workers be in that country. Well, that's not too bad, because you can go in and train welders on pipelines and stuff. It also required employment of other local workers, and the managers could not get visas by law in this country because they had to have 15 years of experience to be able to come in and be a manager, because this country wanted to have good jobs, not just the hourly worker jobs. And the result was, project requires clad pipe. That's the technical decision. The management decision was cancel the project because they couldn't get the people to do the job into the country because of the regulations that were there. So the country had passed these laws hoping to increase the quality of employment, and what they did is they lost a multi-billion-dollar project and all kinds of tax revenue because they formed regulations. We talked about Rhodesian chrome oil before. Another externality is transportation. And it might be fairly mundane, but copper tubing, like we use for water pipe, okay, in homes and whatnot. We never lost that business in the United States. It turns out all you have to have is an extrusion press that extrudes the copper, turns it into a tube, and then you draw it. It really doesn't take a very large building the size of the student center would be able to produce copper tubing. But we kept this industry in the United States. There were, in the mid-1990s, there were 5 companies still making copper tubing in the United States, and the reason is you couldn't afford to transport all that air, okay? It just didn't, you could afford to transport copper around the world as solid copper, but when you make it into 95% air, it turns out it's cheaper just to bring the copper from Chile to the United States and extrude it, okay? So the transportation costs kill you. Another industry where the transportation costs kill you is, and we'll see this in a little bit when I get more quantitative on things, the cement industry. I mean, cement goes for $20 a ton. So you can't afford to transport it very far, and so there's cement kilns all over the world. And that goes for some other industries. Another transportation externality, although you could call it an energy externality, is what the British brought over here in the 1600s to North America. They were having an energy crisis in Britain. And the energy crisis was the fact that they were tearing down all the forests in England for 3 things. One is they needed the big trees to make ships, with the big masts and things like the Constitution and stuff. This was the 1600s, 17th century. And the other thing is they needed to make charcoal to make iron. And they needed that for military reasons too, the cannon barrels and cannonballs and whatnot, and other utensils and stuff. The other thing that came along was glass, and we'll talk about glass a little bit later in the course. But so what were 2 of the things that they brought over very quickly? Because let's remember, what was Plymouth Rock was, I don't remember, it was 16. Jamestown was 1607, and Plymouth Plantation was like 1612 or something. Well, by the 1630s, both of them, Jamestown, Virginia, had a glass works, and there's a recreation. You can go down to Jamestown, Virginia, and you'll see a glass lab, very similar to what we have in the basement of Building 4 here. But it's kind of old time. You go up here to Saugus, Massachusetts, you'll find an iron works, and this was the first iron work in the United States, and they came to both these places because we had trees. And it was an energy crisis, transportation crisis. They were having fuel problems in England, and so the first industries they brought over here were the industries that consumed wood. Okay? So that's the end of externalities. Let's talk a little bit about cost and availability. And so Professor Sadoway used to tell me jokes from the Soviet Union or the Ukraine, and here's one. Someone goes into a store in the Ukraine and says, "How much is that doll on the shelf?" And the guy says, 500 rubles. And he says, "Well, the store next door is out of stock, but they have it for only 300 rubles. And the guy says, "We'll come back when we're out of stock and you can have it for 300 rubles. Cost is important. And I remember there's a faculty member in this department who's very well known as an entrepreneur who started a number of companies. And I remember 25 years ago walking across campus with him. We were walking right past the Great Sale, and he said, "Did you read Joel Clark's article in Journal of Metals this month?" I said, "Yeah." He says, "Well, I never thought about it before, but cost really is important, isn't it?" Okay. Well, this is when this guy was an associate professor, and now he's supposedly the great guru, one of the great gurus of MIT in starting new businesses. I think he's learned that cost is really important, but the point is most faculty don't have a clue about what something costs. And so I'm going to get quantitative here about the costs of various materials that we might want to select. So this is a plot from Michael Ashby that he put together about 1980 or so. And it's materials usage over time. It's a very nonlinear plot from 10,000 BC up to 1000 AD to 1940, 1960, anyway, up to 2020. And he's now got it in color, and he puts across the top Stone Age, Bronze Age, Age of Steel, polymers, molecular engineering. Of course, he was predicting the future here. It's very difficult to predict the future, especially. Prediction is very difficult, especially if it involves the future, okay, is what Niels Bohr said. But they had metals, polymers, composites, and ceramics and glasses back in the Stone Age. Only the polymers and elastomers were wood and skins and fibers from plants, and composites were straw and brick, and ceramics were stone and pottery, and metals were gold or copper. Then we got more and more sophisticated and more detailed in our materials development. And when he wrote all this, metals were sort of peaking in terms of importance in the 1980s. But he was predicting a decline. This is actually a decline in metals, and then a great expansion in some of these other things, particularly ceramics and glasses. These predictions were wrong, okay? And anyone who knew anything about the properties of materials would realize they were going to be wrong, and we're going to talk about some of those. Some of those properties have to do with the cost and availability. So far as native availability, this is a plot of the elements in the periodic table as they are found in the Earth's crust as a fraction of 1,000,000 silicon atoms. So here's silicon right here. At 1,000,000 silicon atoms, it's basically one of the highest except oxygen versus the atomic number. These are basically rock-forming elements. Here are a lot of the well, actually aluminum and iron are two of the metals we use, copper and zinc. Zirconium. Here are the rare earths. The rare earths are actually not so rare. They're at about 0.1% of the volume of silicon or iron in the earth, but that's still quite a bit, and a lot more than the precious metals, the rarest metals. It says the rarest metals here, but in fact, there are 3 metals that are even more rare. Anybody know what they are on the periodic table? They're the 3 that don't really exist on Earth. Okay. Well, you could take the transuranic elements, but polonium, which is extremely rare and is actually a byproduct of a nuclear reaction of another elements. I can't remember which ones. Francium, which is the same thing, and technetium, which has only been seen in the stars, but is used every day in hospitals. In fact, I think I mentioned the other day, about 2 weeks ago, I had a technetium study of my heart. I went to Mount Auburn Hospital and they injected me with technetium-99 with a half-life of about 10 hours. And I was just glowing, okay? And they could take a picture, a radiograph of me glowing and my heart pumping and things like that. Okay, but technetium and polonium and francium would be down off the chart at the bottom of this thing. If we look at the percentage, oxygen is the most abundant in the Earth's crust. It obviously is not the most abundant in the atmosphere. It's nitrogen, but it's the second most abundant in the atmosphere. But this is in the Earth's crust, the solid. Silicon is second, and the two of these compose about 75% of the Earth's crust. Aluminum is very, very abundant in lots of things, as is iron. And you see these things start dropping very quickly. And they're in all kinds of forms of oxides and sulfides, which leads us, not in this course, but in some other modules, into the corrosion of metals, which is one of their Achilles heels. Now this is a plot that I've redone, but this is the old one. This is the original one from a proprietary 1960 General Electric report done by a graduate of this department, Bert Westwood, who looked at the pounds per year versus the dollars per pound of structural materials. And it turns out stone is way up here. It's the most widely used. Cement, back then in 1960, was the most widely used. Carbon steel was actually ahead of cement. It's no longer. Wood. So those are what I call the billion ton per year club. They weren't quite a billion tons 50 years ago, but they are now, and we'll see that later. And you go all the way down here and you get diamond, which is a structural material. It's not exactly something we use in large size, but it's a structural material because we use it for grinding and cutting. And we're using it for its mechanical properties, okay, of hardness and wear resistance. The interesting thing to me when I looked at this is these dotted lines are the ISO market size line, and they have a shallower slope than the usage. And that means that if I could cut the material price by a factor of 2, I will double the volume of material used in the long run. That may not be true in the short run of 5 or 10 years, but over 10 or 20 years, if I could cut the price of one of these materials by a factor of 2, the market volume will increase by a factor of 4. Based on these slopes. And so I will double my market size if I can reduce the cost of production of a material. Okay? That's a long-term trend, and this plot still applies. I had it redone. I haven't had the plot completely redone. But anyway, if you want to look at today, the big cost driver is energy. If I went back to the 1880s, what was the material that drove the world's economy from the 1880s till about 1960? Steel. Andrew Carnegie was richer than Bill Gates back in 1880 in constant dollars, and he made it all in the steel industry because it was the Industrial Revolution. They were starting to build steel ships. They were building railroads. Railroad was actually the big industry. And then along in 1900 comes the automobile. Steel basically was the commodity. And you don't remember it, but I remember as a child in about 1962, I think it was, President Kennedy stood down U.S. Steel. U.S. Steel wanted to raise the price of steel by 10%. And he said, no. The President of the United States told the company. Now, he didn't have the authority to do that, other than the moral authority. He was the President of the United States, and people back then used to respect the President of the United States. But that doesn't exist anymore, but because of some of the presidents we've had since. But nonetheless, it was a big showdown. Was U.S. Steel going to back down? U.S. Steel said they needed a price increase because the cost of digging coal out of the ground and iron ore and everything was going up. And he said, it will cause worldwide inflation if you add a 10% increase in the price of steel. And in fact, U.S. Steel backed down, didn't raise the price of steel, and they claim that that's what destroyed the steel industry. I happen to have worked in the steel industry, and I will tell you that's not what destroyed the steel industry. Maybe they weren't as profitable as they wanted to be, but what destroyed it was bad management. Okay? For example, after World War II, the United States controlled 75% of the world's steel industry. Do you know why? They had bombed out the rest. It's a wonderful thing to go to war and bomb out your competition, okay, in the marketplace. You can become the best in the world. And they had that attitude. When I went to work for them in 1974, they still had the attitude that they controlled 75% of the world's steel market. At that time, they controlled 25%. Today, they control 10% or less. Actually, it's less now. But in any case, today, after 1973, and the Arab oil embargo, the world economy is denominated in oil or energy. And it's not just oil anymore because there's other forms of energy that we have. But basically, the energy is what determines the price of most materials. When I went to, well, later I will talk about, if we do that part of this course, talk about originally at the time of Saugus Iron Works, 90 or 95% of all the cost of cast iron was basically labor, okay? Took about 4,000 hours, 2 person years per ton, okay, to make steel or make iron. Today it takes 20 minutes. Okay, and if that iron worker or steel worker is making the equivalent with taxes and everything of $80 an hour, not that he takes home $80, but if that's what it costs to employ him, in 20 minutes it's 1/3 of that, so we're talking about $25 a ton is labor and the rest of it's raw materials. In the mid-1970s, when I worked for a steel company, it was 50-50. At Bethlehem Steel, it was 45% labor, 45% raw materials, and 10% profit. Okay? So just in a very short period of time, over 400 years, it's gone from 95% labor to 1975 is 50% labor. Today, it's down to about 10% labor, and most of it's raw materials. And the price of a ton of steel today is less in constant dollars than it was in 1975. But a lot of this is due to the energy density. And if we look at the energy density, apologize for the size of the lettering here, but this lithium-ion batteries we hear everything about, okay? This is megajoules per kilogram or megajoules per liter in volume or weight. And lithium-ion batteries bite the dust down here compared to other things. Chemical energy, such as coal, anthracite, okay, or plastics, if you burn the oil, have much higher energy densities. And if it's got liquefied natural gas, it's got kerosene and gasoline. Okay, so here's your chemical energy. And now you know why automobiles have traditionally not been electric vehicles. You had a much higher energy density with gasoline, chemical energy, than you did with electrical energy. President Obama, when he became president 10 years ago, said we're going to have a hydrogen economy, and people will be driving vehicles that will be environmentally safe because they'll burn hydrogen with oxygen and produce water vapor. Okay? Great idea, Barack, but how are you going to do it? Okay? There's a little technology problem there. One of the problems is how do you store the hydrogen? Okay? And they have given away hundreds of millions of dollars trying to figure out a way. And this is hydrogen at 700 bar pressure, 3,500 psi. And they look at things that are even bigger than that. So you want to be in a car that has a pressure vessel full of hydrogen at 5,000 psi, and you get in a wreck, And if it breached, all of a sudden you got a big fireball. Plus you got a big boom, okay? You might survive the crash, but you want to survive the explosion or the fire, okay? So there's a little problem there, okay? It turns out there's a student who's defending his thesis over mechanical engineering on Friday, where he's been basically taking aluminum because everyone knew that aluminum was way up here in energy density, and the aluminum basically can generate hydrogen. He basically takes little aluminum spheres, ball bearings, and he treats them with a indium gallium alloy at about 2 or 3/10%. He treats them a certain way, and he drops them in water, and within 10 or 20 seconds, they all convert to hydrogen and oxygen just by corrosion. Very rapid corrosion process. So people of years have called aluminum canned electricity. When the former Soviet Union broke up in the 1980s, they had tremendous hydroelectric capacity in Siberia, and that's where they would produce their aluminum. And they needed foreign exchange, and they would basically generate the electricity in Siberia. Couldn't get it out of Siberia unless they made aluminum, and they started dumping aluminum on the world market for half the price that Alcoa and other people made it, because that was the only way they could transport it out, okay? So if we start looking at energy content in megajoules per kilogram, we find aluminum is way up above most other things. Your plastics, which you can think of crude oil, if you want, is of less than half, anywhere from 25% to 50% of the energy content of aluminum metal. And by the way, aluminum metal, if you want to have a hydrogen-fueled vehicle, rather than pump hydrogen into some pressure vessel on the car that could explode in a crash, if all you have to do is go to the filling station, pick up some aluminum ball bearings and some water, and then mix them together later as you need them, dropping ball bearings into the water to generate hydrogen, that's a lot safer. In fact, I remember when Obama came out with the announcement that we were going to have a hydrogen-fueled economy, and people were talking about you'd go to the filling station and you pick up your hydrogen. I thought, there's going to be a lot of burned people. Anyone ever seen a hydrogen flame? What's it look like? It's invisible. What's burning? It burns to H2O. And the thing that makes a flame orange, what makes a flame orange or yellow? The little unburned soot particles in the flame. Okay? Hot steam doesn't have any, it might distort the air a little bit, but if you go to a refinery where they use hydrogen all the time, people have walked through leaks where you have a hydrogen leak that catches fire, and they just walk through it because they didn't even know it was there. It's invisible. And I thought, boy, this would be great. People filling up their cars at filling stations where you could have leaks and flames and people just go walking through them. Anyway, aluminum has a very high energy density, and it could be a good way of storing fuel for a hydrogen economy if you wanted to have it. Steel is 1/5 of aluminum, and that is essentially the price differential between steel and aluminum. I told you energy is the big driver. Well, it works out that steel goes for about 50 cents a pound, or 40 cents a pound, and aluminum goes for about $2 a pound.
Is that 250, is that actually accessible, like energy in terms of the hydrogen process?
Johnny's getting over 90% conversion, okay? But that, you're right, your efficiency of converting the aluminum to whatever other fuel is an important criteria. But he's got his energy content of the hydrogen, he loses 10% in the chemical reaction and stuff. So it's still pretty good. Oil is down here, okay? Same price as steel, basically, per kilogram. Coal, cast iron, glass, cement, wood, and stone. I don't know if you remember, but I told you the billion ton per year club was stone, wood, cement, and steel. Well, it turns out The least expensive materials are the materials that use the least energy, except for steel. And steel has about 10 to 50 times the properties of stone or wood in terms of mechanical properties as a structural material. So we can afford to pay more for steel because it has better properties, but these are the only ones. And so it turns out, what drives the usage of material? The number one thing, folks, is cost. Okay? Yeah, question?
What's coming out in the recycle?
Recycle, that's the energy to reprocess. So if I want to take aluminum cans and turn them into automotive body sheet, it takes 15 megajoules per ton, whereas to get it from aluminum oxide takes 250. Okay? And so steel, it takes 20% of, if you start with virgin iron ore and limestone and coal, 50. Recycle it, remelt it, 20% of that. Because you've already gotten the oxygen out.
Yeah.
Okay? So the recycled number here. And by the way, this is something I produced. I couldn't find anything like this in the literature. But the numbers are real. I mean, I spent a lot of time going out to get these numbers. So we can look at strength versus energy content of a material. And if we're talking about structural materials, okay, energy content is the same as cost. Hopefully I just explained that to you. Here's the strength, and this is what's called an Ashby plot today, after Michael Ashby, who was a professor at Harvard. Now he's gone back to England, and he's retired, but he's making a lot of money because he came up with this. He wrote these excellent books on material selection, and he has a company that sells software program, Granta, that you can buy for $30,000 that will help select materials for you. It's not all that great, folks. Okay, it will select them, but it doesn't put in. Artificial intelligence is not there yet. Okay, to be able to really select the right material. You still need to hire a consultant like me. Oh, sorry. Anyway, so this is the energy versus the strength, and you can see the metals out here. You want to be way out here. High strength. Oh, I'm sorry. Is embodied energy. So actually, you really want to be over this side. You want to be high strength. You'd like to be over here, okay, in this quadrant. Metals are expensive, but they have high strength. Bamboo is this wonderful material. Okay, some of the natural materials are actually getting to be the lowest cost and the highest strength. Stone and brick are very low cost, but very low strength. And there's all your other materials. Turns out Ashby's plots on lots of different material properties show that most materials go over about 6 orders of magnitude. If you take all the materials, structural materials in the world, okay? If you want to look at another thing like thermal conductivity versus resistivity, this one actually goes over about almost 7 orders of magnitude, but in any case, your metals are way over here, your polymers are way down here, glasses are over here. So an Ashby plot is like a 50,000 foot view of material selection, which is why the Granta program doesn't really work for details things. You want to be a little more accurate than 10 or 20% of the best material, particularly since it's your whole economy or whatever is going to be based on picking the lowest cost material, and just being 80% correct is not good enough. But nonetheless, the Ashby plots really do help place different classes of materials. And when we get to strength and toughness, which we will later, you're going to see why some materials are the materials of choice. And which are the materials of choice for structural materials? I mentioned this a couple of times now. Again, this is my numbers. I researched this within these numbers from the last year. But the stone manufacturers say it's 53 billion tons. I rounded it off to 50. Engineered wood products, the people who make engineered wood products, that association says they sell 3.5 billion tons. That's not all the wood in the world. All the wood in the world is probably is 50 billion tons, but most of the wood is not engineered wood products for structural beams. Most of it is going into burning and heating homes in the third world and stuff, okay? Concrete has passed steel. It's 2.2 billion tons, and that's actually the cement. The concrete itself, with all the stone in it, is actually about double that. 50% of the weight is stone, so some of that stone goes in here, but it's a small fraction of the stone. If you want to talk real concrete, I should probably change that to cement. The binder that's made from the calcium carbonate and other things is 2.2 billion tons. As recently as 10 or 15 years ago, that was about 2/3 of steel. It was around 600 million tons, and it has been growing rapidly as the third world becomes more wealthy. They really can't afford steel buildings, but they can build concrete buildings. And steel continues to grow on a steady slope of about 2.5% a year around the world, and it's at 1.5 billion tons. And I think I mentioned to you the structural material could be plastics at 300 billion tons, but if I'm talking metals, it's aluminum at 45 million tons, okay? It's hardly in the running. 95 pounds of every 100 pounds of metal made in the world is steel. And students get tired of my saying that steel is an important material, but it's only important because the economics drive it, as well as properties, okay, the strength and toughness of steels. But there is a reason why steel is so big, and there's a reason why Andrew Carnegie was the richest person in the world at his time. If we start looking at tons per year of a lot of different materials, you can go to the U.S. Geological Survey, and they do their little annual review of different materials. There's a lot more than just these, but these give you some of the numbers. This is all plastics, anywhere from polyethylene to high performance aerospace plastics. You lump them all together, and there's still only 20% of steel. Although, as my old thesis advisor used to say, in volume, they're approximately equal. Okay? Is that what you were going to say?
Yeah, I was going to say that this metric kind of is weighted towards steel.
Well, on weight, because one of steel's Achilles' heels is it's too heavy. Okay, and we're going to get to that. Okay? But that's this metric. I have another metric coming up, okay, which is dollars per ton. Okay? But I put plastics in here with a bunch of metals. Turns out iridium, if you went back to that abundance in Earth's crust, iridium is one of the, except for polonium, francium, and technetium, iridium is the least abundant metal in the world's crust, which is why I made my wife's engagement ring out of 80% platinum, 20 iridium. Actually, that's not the reason, but actually it is part of the reason. So if we look at dollars per ton, you start seeing some other things, but it turns out steel still leads the list on a dollars per ton. Plastics are more expensive, but plastics still have advantage. I'm not, and we'll get to the other properties. Aluminum is 4 times the price because it's got 4 times the energy content. Plastics are considerably higher because they have about 5 times the energy content just for the crude oil value. Okay, if you just burned them, you're going to get that much energy. Copper is not found in very rich ores anymore, and so there's a lot of getting around the entropy problem of concentrating the copper. And you come down here, and some things like nickel-based superalloys, they're fantastic mechanical properties, but they're kind of pricey. Same thing with titanium, although it doesn't always have such fantastic mechanical properties. Neodymium, which is essential in some of our functional magnets. Gold, way overpriced, okay? But they'll pay you good rupees in India for gold. Iridium at $17 million a ton. Scandium's kind of interesting. $4 million a ton, and there's only about 2,000 tons a year. And here is one of the largest, if not, well, I don't know if it's the largest, use of scandium. It says right here, scandium alloy, 100 KSI aluminum, 30% stronger than what goes in a Boeing aircraft wing, okay? And it turns out that there's a lot of money in baseball bats, okay? And that's why if you add 0.2% scandium to an aluminum alloy, you just double the price of the aluminum alloy, because you're paying, what is it, scandium, $4 million a ton, which is 20, how much is that? That's $2,000 a pound, okay? So you start figuring out the cost of aluminum alloys with scandium. But it turns out scandium refines the grain size like nothing else. The Soviets tried this. They weren't worried about economics 30 years ago. And they showed that scandium can really improve the properties of aluminum alloys. And so it turns out people are looking to see if they can drop the price of scandium, because it's not a rare element. There's a lot of it out there in the world. It's sort of dispersed. You got the entropy problem, but some of the Japanese companies, one of them, which, well, I'll tell you, Sumitomo was announced, they will produce 100 tons of scandium oxide a year. That's what they've announced, and they actually are probably going to produce a lot more than that from some of the other processes that they have. And so people are looking at this to be able to increase the strength of aluminum in automobiles. But you can't just double the price. We're going to get into that, of an automobile alloy. So relative cost and density. Now, this is where, I don't know, I didn't put the plastic on here, but the plastic would show up very well here if we had relative cost and relative density. And you look at some of these things, people say, well, use titanium or use cobalt alloys or nickel alloys. Well, these things are a little pricey compared to the workhorse materials of steel and aluminum. And I always thought this was interesting. The price of copper, if it's $10 a pound, order of magnitude, silver is about $1,000 a pound, and gold's about $100,000 a pound. Just go up by an order of 100 each time between copper, silver, and gold. Just going down the periodic table.
Why would people, like, I see nickel a lot in, like, cheap jewelry and like cheap metal alloys. Why would they be using that if it's like 50 times more expensive than steel in relative cost?
First of all, it's plated nickel. It's not solid nickel. They're putting a nickel flash on there. And the reason is nickel will electroplate better than any other metal in the world. And so if you want to get a good gold plate, you put a nickel flash underneath it, because aluminum and steel have these precipitates and carbides and things. You can lay down pure nickel. It's a beautiful material to electroplate something else on top of. So that's now nickel is a little bit of a problem because it can be toxic. It is toxic in the human body, and some people are actually allergic to it. I mean, I have a daughter who's even allergic to gold and platinum. She doesn't have pierced ears. She always wanted pierced ears when she was a teenager. She got pierced ears. That lasted for about 2 weeks, okay? And even platinum. And a lot of people, some people cannot tolerate silver, can tolerate gold, but if you can't tolerate gold, you go to platinum, and one of my daughters can't even tolerate platinum as, you know, in her skin.
Well, I guess the other thing is nickel, when it's up against the jewelry majors, is cheap. Right, it's virtually free.
Oh yeah, yeah, yes. Compared to gold, it's peanuts. In fact, so we can use nickel. We can use pure nickel underlayers. We usually use brass, so we're using copper, which well, here's copper, so it's cheaper than nickel. But we use cupo nickel and a lot of things, brass, and then we put gold on. In fact, Attleboro, Massachusetts is the gold capital of the world because in Sheffield, England, they came up with a way to braze silver to base material brass, and they could make silver plate. And so now people could own not sterling silver, but silver plate dinnerware and stuff, and they could pretend like they were rich, okay? But then in Attleboro, they said, oh, we can do this with gold, and they made gold-filled material. And there's a company down there, it used to be called Leach & Garner, and I actually started consulting with them in 1980 or 1978, I guess. And it was the sons, Phil Leach and Steve Garner, of the founders in 1899. The reason Attleboro is the gold capital of the world is because they had the mill that made all the stuff. They had, when I was there, they had 3 continuous casters for gold. And they went through 7 tons of gold a year, okay? And that's why Attleboro is the gold capital of the world. Because you're making composites basically out of metals. because of the cost for jewelry. Okay. Other questions? Oh, okay. So strength versus relative cost. Here's an Ashby plot, only over 5 orders of magnitude. And you can see technical ceramics are now we have relative cost per unit volume. The technical ceramics are very expensive. The non-technical ceramics like concrete are very inexpensive. The metals are actually sort of here. Well, actually they're all through here, but the common metals are over here at a relatively low cost, but not necessarily the highest strengths so far as that goes. But this gives you the ballpark of what's available in the world, okay? Now another thing this is, again, one of the things that I came up with. Now other people had done some of these things, but I sort of integrated all this stuff to say value of weight saved over the life of a vehicle. If we're talking an automobile, if you talk about $2 or $4 a gallon gasoline and you talk about an automobile that goes for 100,000 miles, you'll save $2 per pound. This is for like a 3,500 pound vehicle. And there's plenty of data to support that. If you go to ship or rail, it's a factor of 10 cheaper, and the typical lifetime of the ships or the railroad cars is about 30 years, okay? But you only save 20 cents a pound because they roll or they float and it doesn't take a lot of energy to move them. Aircraft, it's about $200 a pound over 100,000 hours. Typical commercial jetliner will run for about 100,000 hours before they decide the maintenance costs are getting too steep and you just go out and buy a new one that's more energy efficient and everything. Spacecraft, we talked about this, about $20,000 a pound for payload in orbit, okay? You have to know what industry you're talking about if you're talking about selection of materials. And most of the material scientists have no clue. Actually, they do have a clue. They just don't want to tell you, okay? They think they're going to sell all their material into the spacecraft industry. Well, that's ridiculous, okay? Or they think everything's going to go into the automotive industry. Well, it turns out if you take that $2 a pound or 20 cents a pound in ship or rail with 1,500 ships made in the United States or 70,000 rail cars, you're talking two industries of $20 billion each. If you talk aircraft, you're talking about $150 billion. Now, Boeing actually is about 1/3 of that in the United States, but there are other people like Bombardier or Learjet or various others, okay, that use aluminum in aircraft. The spacecraft industry, they only make about 100 satellites a year, folks. And they may be fairly expensive satellites. They may cost a couple $100 million a piece, but that's only a $20 billion market. The reason everybody wants to get into the automotive business, this is the Walmart of materials, okay? This is the big volume. 30 million vehicles, 600 billion a year. That's just the United States. That's not world. If you want world numbers on these, multiply each one of these columns by 3, because the United States is about 1/3 of the world economy. So the sweet spot is automotive. A lot of people shoot for automotive, and they shoot for it with something that's just too expensive. If you start looking over time in the U.S. economic sector, in the 1800s, this is a nonlinear time, in the 1800s, 95% of the workforce was involved in agriculture, just trying to feed themselves. And then you had some small amount of industry. This was kind of artisans of blacksmiths and coopers and potters and things like that. And right at the top here, there's a little bit of service sector and whatnot, or the government. The 1850s, you started seeing the Industrial Revolution. That's this red stuff, which is now decreasing as we basically become more and more productive and need fewer and fewer people to produce even more goods than we did before. The service sector is huge. The government sector is exploding in size. And so we have had a tremendous, just in a generation or 2 generations, we've had a tremendous displacement. This may be not disruptive technology, if you know Clayton Christensen's book, but it's certainly disruptive in the entire industry. If I start looking at where the money goes for a fabricated structural material, material scientists don't admit it, but only 10 to 20% of the cost goes into the material. The vast majority of, so if I'm talking about an automobile that's going to sell for $25,000, it turns out the materials cost is only going to be about $2,500 to $5,000 max that goes into that $25,000 car. Most of it goes into design and engineering, or the biggest fraction is in fabrication, sheet metal stamping, joining, forging, machining, all those manufacturing processes. Or if you want to throw in there, non-destructive testing and quality control is equal to the materials cost. If I was Lee Iacocca, I'd tell you that health insurance is $5,000 of every car, okay, for the auto workers. General administrative is about 10%, and profit, if you add all these up, is anywhere from losing 10% to gaining 10% profit. But if you take these types of numbers and you say, okay, the value of a pound saved in an automobile is $2 a pound, 10% of that as a material cost is 20 cents a pound, okay? And I'll get to all that in a second, but it turns out there's only a few materials that you can use at these levels. If I start looking at material cost as a fraction of the total cost, automobiles and aircraft, which is $750 billion of our manufacturing products that we were talking about, the vast majority, it's about 10% is the material cost. The two industries that I know of that have the highest material cost as a fraction of the product you're going to build are stationary things, pipelines that get buried in the ground, or utility transmission towers. Those will pay more for material, up to 30%. Spacecraft, material cost is nothing. Semiconductors is even less, okay? So for structural materials, it's about 10%. And if I take and say, okay, if I'm going to I have to have materials that cost no more than $2 a pound, and 10% of that can be my material cost, my only choices to build a ship are steel, wood, or concrete. For an automobile, it's steel. Now, if I say I'm going to spend up to 20% of my cost on the material for this thing, like an automobile, I can throw in aluminum and plastics. If I want to do aircraft, I can go for aluminum at 10%. If I want to pay more, I can add composites. Spacecraft, I can certainly do composites, and if I really need something, and I do need refractory metals in spacecraft because of their low coefficients of thermal expansion and things like that. But nature has chosen the materials based on cost and based on the savings per pound, okay? And you notice, I know you like plastics, but plastics, they're in automobiles, but you're not going to start making plastic automobiles unless you're talking racing cars. And we've been doing that for years, okay? But those are $500,000 vehicles or $1 million vehicles. It's not your $25,000 Ford Taurus. Okay, so maybe I'll conclude with Sprague's law. The head of materials at GE Aircraft Engines in Cincinnati for many years he had a lot of great sayings. He was just a great engineer who would say it like it is, okay, and didn't worry about who he offended. Whenever you first hear the properties of a new material, write it down, because those are the best properties the material will ever have. So all you material scientists who think you've just invented the world's greatest material, and you tell me how wonderful it is, well, I'll take down notes on what your properties are, because you got it once, you'll probably never see it again. And Jim Williams, who replaced Bob Sprague in that job, says whenever you hear the cost of a new material, write it down, because that's the lowest cost the material will ever have. Okay, so people are always very, very energetic, enthusiastic about their new material, but the cost and the properties of new materials never quite make what they're originally hyped up to be. So I'll see you tomorrow, and we're going to start talking about speed versus cost in selection of material.